Okay, so now I'm going to go ahead and go through number 9 from chapter 5 from the Physics 1 textbook. So on this one, there's a really key concept that this one covers, which is why I wanted to go over this. There were only not very many of you who had questions on this one, but the fact that mass doesn't play a role in the acceleration is a really, really important concept and something that you should definitely know or be able to prove. So that's why I wanted to go over this one. So it says, show that the acceleration of any object down an incline where friction behaves simply, that is, friction is fun. So friction, kinetic friction is mu, kinetic value of mu times the normal force. So fun, friction is fun, that's how I remember that one, is A equals G times sine theta minus mu k cosine theta. So we want to find the acceleration, and then we want this to be our answer, is what they're saying here. Okay, so first we go ahead and draw a diagram of an object sliding down an incline. I'm gonna fix that a little bit. Okay, so here's my object, and I'm just going to draw a basic force diagram for it. So here we have the force of gravity, and we know that it equals mg. Perpendicular or normal to the surface, we have the normal force. And then resisting the motion, we have the force of friction. I'm trying to use the same... There's all these different ways that you can write this stuff. I'm going to try and keep it consistent with the book. Okay, so what we want to do on problems like this is we want to turn our XY axis usually. So you have to think about, like, where does it make sense to have your XY axis? Usually on these incline problems, it makes sense to turn it because now the normal force is on my y-axis and the force of friction is on my x-axis. And the only thing that's off of an axis is the force of gravity. So I've got 2 on and only 1 off. So that's a good thing. So then we can break up our forces and look at what's going on in each direction. So we can say the sum of the forces in the y direction is the normal force minus the y component of mg. So that is going to be, if we look at our trig friends, if we're looking at this angle here, this is our adjacent, so this is going to be minus mg cosine of theta. Okay, and we know that this equals 0 because our object is not jumping up or sinking down into the ground, right? So then we can say that n equals mg cosine theta. Then we can look at the sum of the forces in the x direction, and we can say that we have the x component of our gravity. So that's going to be the other one, right? That's going to be mg sine theta, that other component, minus the friction. But now we need to know this friction, so we can go back to our fun equation, and we can say that Fk equals mu k times the normal force, which is mg, times the normal force, which is mg cosine theta. So now we can plug that into here, and we get the sum of the forces in the x direction equals mg sine theta minus mu k mg cosine theta. But we don't want to know anything about the forces in the x direction. We want to know about the acceleration. So if we look at our fun sum of forces, it's mass times acceleration. So acceleration is the sum of the forces divided by the mass. We're just looking at the x direction because that's the only place that the motion is happening. So our acceleration is going to be equal to all of this divided by the mass. So this is where it gets magical. Minus mu k mg cosine theta divided by the mass. So A equals, and then we can factor out an mg in the top. Mg sine theta minus mu k cosine theta over m. So then our m's cancel and we just get that A equals g times sine theta minus mu k cosine theta. And you see that we end up being able to find our acceleration without even knowing the mass, which is pretty crazy and pretty awesome. All right, I hope this helps.